So in this video, we're going to talk about inverse matrices and specifically in a little while how to use inverse matrices as an additional method to solve these linear systems. So to get started though, we need to first talk about the identity matrix. Now, as a definition, the identity matrix is an n by n matrix, which if you remember, an n by n matrix just means it's a square matrix with ones along the main diagonal and zeros everywhere else. So a square matrix with ones along the main diagonal and zeros everywhere else. So for example, the 2 by 2 identity matrix would look like this, where we define the main diagonal as this part right here, and then zeros everywhere else. The 3 by 3 identity matrix would look something like this. Again, you can see our ones are along the main diagonal here, and zeros everywhere else. So we could keep going as far as we needed to, depending on the circumstances, but it just needs to be a square matrix to get started. So the identity matrix is very important in the world of matrices. Once you get finished working the example that you see, you'll hopefully be able to convince yourself that the identity matrix is actually the multiplicative identity for all matrices, which means that if you take any matrix and multiply it by the appropriately sized identity matrix, you'll end up with what you started with. So now that we've discussed the identity matrix, we're ready to move on to what an actual inverse matrix is. So to define this, we'll have to start by letting A be an n by n matrix. So matrix A is itself a square matrix. The inverse of A, and we denote that by A with this upper minus 1. So if we talk functions, function f, the inverse would have the upper minus 1 on it. So similar for matrices. Matrix A denoted A, inverse matrix would be A with the upper minus 1. So the inverse is also an n by n matrix such that A times the inverse equals the identity, which equals the inverse times A. Now that's a pretty powerful statement actually, because from an earlier section we saw that matrix multiplication is not commutative. So what we're saying here is that if we've chosen and we found the inverse matrix correctly, that when you multiply the inverse by A in either direction, you actually do end up with the same thing, and in fact that thing is the identity matrix. So now to find the inverse matrix, and you'll want to keep in mind not all matrices are invertible, similar to functions. Not all functions are invertible, but to find it, we would take matrix A, we would augment it with the appropriately sized identity matrix. We would use our elementary row operations. And our goal would be then to put the identity on the left-hand side, and whatever was left on the right would actually be the inverse matrix. So we'll go ahead and take a look at an example. Given matrix A, we're going to find the identity, and so I will take matrix A, which is 1, 4, 3, and 8, and I'll augment it with the appropriately sized, in this case 2 by 2 identity matrix. So we'll handle this the same way as before. We'll start in column 1. We'll make sure we get our 1 in place. We're good. Now we need to get our 0, and we're going to do so by using the 1 in the column. So a -3 row 1 plus row 2 gives us a new row 2. So our top row does not change, but our bottom row now, we'd have a 0, and then we'd have a -12 plus 8, so -4. then we'd have a negative 3 plus 0, which would be a negative 3, and a 0 plus 1, which would be a 1. So column 1 is complete. Now we're ready to move over to column 2. We need to get our 1 in the correct spot, so we'll need a negative 1/4 times row 2 to get a new row 2. I'll keep that first row the same again. We'll have a 0, a 1, a 3/4, and a negative 1/4. Now that we have our 1 in place, still in column 2, we'll need our 0. So this would need a negative 4 row 2 plus row 1 to get a new row 1. We'll keep that second row now alone. In the top row, we'd end up with a 1, a 0, a negative 2, and a 1, which means that the inverse we just found is the 2 by 2 matrix, negative 2, 1, 3/4, and negative 1/4. Now we're actually able to check this. If you look back at the definition, we know that if this truly is the inverse, then the inverse times A in both directions should be the identity matrix. So to check, there's two things we would need to show. We would need to show that matrix A, which is 1, 4, 3, 8, multiplied by the inverse, which is negative 2, 1, 3/4, negative 1/4, that should give us 1, 0, 0, 1. And we would also need to go in the other direction. We would also need to show that if we take the inverse and we multiply it by A in that order, we still get the 1, 0, 0, 1. So take just a second and go ahead and confirm that, and then you'll be ready for the next example that you can try. All right, so now we're actually ready to start solving linear systems using inverse matrices. And to show you how this is done, we're actually going to go back into a general form of our matrix equation. From before, we defined our matrix equation as AX equals B, where A was the coefficient matrix, X was the variable matrix, and B was the constant matrix. Now, if we treat this almost like an algebraic equation, our job is to get X all by itself. So essentially, we need to remove the A. Now, we have to remember these are matrices, so we can't just go dividing by something. Instead, we're going to take advantage of these inverses. So the first thing that I'm going to do, starting with this equation, is I'm going to go ahead and multiply both sides by the inverse. Now we do need to be a little bit careful. If this was a typical equation where we had something like 2x equals 3, multiplying both sides by 1/2 is a pretty clear way to get your x equals 3/2. But in dealing with matrices, because multiplication is not commutative, we have to make sure to multiply the same side of both sides by the same thing. So let me show you what I mean. If I multiply, as you can see, the inverse matrix to the left side of the left side, I need to make sure to multiply the inverse matrix by the left side of the right side. I know that's kind of a mouthful, but let me go ahead and write this down so you can see exactly what it looks like. So this is currently where we are. I've got the inverse, I've got A, I've got X, equals the inverse and B. Okay, so I multiplied the left side of both sides by the same thing. So now you can see on the left side, the inverse times A would give you the identity matrix. So the identity matrix times X equals the inverse times B in that order. And we also know that the identity times X is just going to leave us with X. So our job is complete. We wanted to get X all by itself. We did. So when it comes to these linear systems, when we want to solve them using inverse matrices, all we have to do is find the inverse and multiply it by B in that order. So let's take a look at an example. So in the example we're going to look at, we know that if we're going to find x, we're going to need the inverse times b. And so just to be clear on this, matrix A is the coefficient matrix, so 1, 4, 3, 8. And for us, matrix B, the constant matrix, would be 5, 7. Now, what's pretty convenient is that the earlier example we worked was matrix A being 1, 4, 3, 8. So in this case, we've actually already found the inverse. There's no need to go through the process again. A few minutes ago, we found that -2, 1, 3/4, and -1/4 was the inverse matrix. So we're ready to now say that xy equals the inverse multiplied by matrix B in that order. So finally, when we multiply these things, and it might not be a bad idea to just remind you, this is a 2 by 2 matrix, this is a 2 by 1 matrix, so we can multiply them, and the size of the resulting matrix will be a 2 by 1. So when we actually multiply those together now, we get a -3 and a 2, so that the solution to our linear system is the ordered pair -3, 2. That's where these two lines intersect each other. Okay, so our final example, we've got now a 3 by 3 linear system. We're going to solve using inverse matrices. So the first thing we'll need to do is we'll take matrix A, which is the coefficient matrix. We'll augment it with the appropriately sized, in this case, 3 by 3 identity matrix. And we'll go ahead and perform our row operations so that we try to get the identity on the left, and whatever sits on the right will be the inverse. Once we find that, we can take the inverse, multiply it by the constant matrix in that order, and we should have our solution. So to get started here, we're going to go ahead and focus on column 1. In column 1, our 1 is in place. Now we just need our zeros. So a -2 row 1 plus row 2 gives us a new row 2. A -4 row 1 plus row 3 gives us a new row 3. So I'll go ahead and copy down row 1 since it's not going to change. And then in row 2, we're going to have a 0. We're going to have a -5. We're going to have a 3, a -2, a 1, and a 0. In row 3, we're going to have a 0. We're going to have a -5. We're going to have a 3. -4, 0, and 1. So column 1 is complete. On to column 2. We need to make this a 1. So I'll go ahead and do a -1/5 row 2 to get a new row 2. Keep our first row and our third row the same. This will give us a 0. It'll give us a 1, a -3/5, a 2/5, a -1/5, and a 0. All right, so column 2, let's get our zeros. So this will be negative row 2 plus row 1 to get a new row 1, and 5 row 2 plus row 3 to get a new row 3. Let me move over to this side of the screen here. So our 0, our 1, our -3/5, 2/5, -1/5, and 0. And then I'll go ahead and do the bottom row first. The bottom row looks like we get a 0, a 0. And actually we're going to end up with a 0 there. And finishing out that bottom row, we'll have a -2, a -1, and a 1. And the top row would be a 0, a 0. That would be a -2/3, a 3/5, a 1/5, and a 0. Now, what's just happened is that if we continue this into column 3, we're not going to get a 1 where we need to. And so this line right here suggests something pretty special. That line of zeros on the left side and the -2, -1, 1 on the right will say or will suggest that the original matrix A is not invertible. So A is not invertible, which actually means one of two things. So therefore, either no solution or infinitely many solutions to the system. Unfortunately, it doesn't say one or the other, so it would be up to us to figure that out. So we could decide no solutions or infinitely many solutions by any other method of your choice. You could use regular substitution, regular elimination, Gaussian elimination, any other method that you saw fit. You could make the decision as to which one of these answers it would be. But inverse matrices would not be a technique here that would work, since matrix A is not invertible.